All right, so these are the phases. I ended with what's called the first quarter moon, and then after half of the moon is illuminated, that phase is called the gibbous, and so it's waxing if more than half of it is illuminated, and it's increasing from night to night. And then when the Earth, the Moon, and the Sun are at 180 degrees from each other. Well, the moon and the sun are 180 degrees from each other. That's, of course, for us, that's a full moon. And then what happens is the gibbous, or more than half of the moon is illuminated, but that is getting smaller and smaller as time goes on. And then comes what's called the third quarter, where half the moon, only half of the moon is illuminated, and then it gets less and less, and that's called a waning crescent. Waning, of course, because it's the crescent is getting smaller and smaller and smaller. This phase is the moon that you see early in the morning. If you still see the moon at let's say 8 o'clock in the morning or something like that, that's actually a waning crescent, or actually it could still be a waning gibbous as well. All right, and then of course it completes its cycle, and then we start with a new moon again. That is, the moon and the sun are roughly in the same direction in the sky. Now, of course, the shadow of the moon only hits the Earth when there's, and that's actually called a solar eclipse. That's actually quite rare, because the moon, as it goes around, it's actually tilted by about 5 degrees with respect to the Earth's equator. So usually the shadow of the moon it's always there, of course, but it's usually just cast out into space, and it doesn't cross the Earth. And similarly, that's a solar eclipse can only occur when there's a new moon. Similarly. Then what's called a lunar eclipse can only occur when there's a full moon, and that's, of course, when the moon is in the Earth's shadow. But again, that doesn't happen every single month, because the moon and the moon's orbit is tilted by about 5 degrees, and so the Earth's shadow, which is always there, the moon usually goes either over it or under it on a given month. All right, so those are the phases of the moon. That's the important part of this. This thing talks about the fact that the sidereal day is, of course, a little bit shorter, and that adds up over time. Sidereal is with respect to the stars. That's the only part that's important about that. All right, let's keep moving. Let's try to finish with this video. Finish all these slides with this video. So the phases of the moon. Know the order of the phases of the moon. You definitely want to know that. So new moon, and then waxing crescent. Then there's what's called the first quarter, and then waxing gibbous. Then full moon, waning gibbous, last quarter, which is also sometimes called third quarter, and then waning crescent. And then there's, of course, back to the new moon, where you don't see the moon. Let me mention this as well. The moon's phases are often used in calendars for different cultures around the world. The Jewish calendar, for example, uses or at least part of the Jewish calendar uses the phases of the moon. The Islamic calendar uses the phases of the moon, and in fact, some of the Christian holidays are with respect to the phases of the moon as well. When you might know, or you might have experienced, that Easter changes each year, and it has to do with when the first full moon is after the vernal equinox, which is not going to occur each time. This slide is showing us why eclipses do not occur, and this is actually really nice to see this. So let's say it's a new moon. There's that tilt by a little bit around 5 degrees. And so usually the moon's shadow, which is of course always there, it does not hit the Earth. And similarly, when there's a full moon, the moon is not in the Earth's shadow because of this tilt. Now, when it does, of course, that's when the moon crosses the ecliptic, and that's why they call these eclipses, right? That's where that idea comes from. All right, so that's that. Let's see, lunar eclipse. Oh, yeah. So know the difference between a lunar eclipse. A lunar eclipse is when the moon is in the Earth's shadow, and a solar eclipse is when the moon shadow, which is much smaller. It depends on how far away the moon is. It varies in distance slightly, and so the moon shadow, when it hits the Earth, I think the widest it can be is about 7 or 8 miles across, and it's just a strip of land or ocean, and in fact it's usually ocean, because of course the Earth is mostly water, and so these solar eclipses usually occur across the oceans. All right. And I guess I should mention this as well. So when the moon is in the Earth's shadow and there's a full, a lunar eclipse, the moon actually does not completely vanish. It'll actually turn kind of reddish or orangish, and really that has to do with the Earth's atmosphere. The Earth, as you know, has an atmosphere, and what happens is the sunlight gets refracted or bent around the because of the Earth's atmosphere, and so some of that light, in fact the red light bends the most, and that's why the moon will appear generally reddish or orangish during a lunar eclipse. All right, yeah, that kind of, and of course there's partial eclipses as well. And the only time that you can see what's called the solar corona, the outer atmosphere of the sun, is when there's a total eclipse. All right. This is called an annular eclipse. When you see the moon is not always the same distance from the Earth, and so sometimes when it's a little bit closer to the Earth, and there happens to be one of these eclipses, it doesn't completely block the entire sun, and that's called an annular eclipse. And then of course there's also partial eclipses as well. It's really hard to even notice these, to be quite honest with you. The annular eclipse is a little bit more noticeable because most of the sun is blocked, but because the sun is so bright, you hardly ever even notice this. You actually need special equipment to be able to see this. All right, so this is actually showing you over the course of a year, as the moon goes around the Earth, why there are not always eclipses. So that is showing that. This is actually a way of measuring distances. And this goes back thousands upon thousands of years, called triangulation. So what you do is let's say you're measuring the distance to some distant tree, where you can't get to that tree, but you can use what's called triangulation. And so you measure very, very accurately your baseline, and then you measure angles. Usually one end of your baseline is at 90 degrees, and then you only have to measure this angle right here. All right, and so you measure that very accurately. This is still done today. If you ever look along the side of the road and you see surveyors with their little their little telescopes, that's exactly what they're doing, is they're using triangulation. We actually use this in space. So as the Earth goes around the sun, we can actually see the stars. Well, we don't see it. Let me not with the naked eye. This actually takes pretty powerful telescopes. Only about roughly 200 years ago were we able to have the telescopic technology to be able to see this. Now, telescopes have been around for 400 years, since the time of Galileo, but only roughly 200 years ago were we able to measure what's called stellar parallax, the shifting of a star, a nearby star, with respect to much more distant stars, and that's called a parallax. And so we measure that angle. And this picture is showing you from one side of the Earth to the other. That's not really very accurate with the Earth. The stars are so far away. You actually need to look at the star and then look at it 6 months later when it's on the other when the Earth is on the other side of the sun. And so we use that as our baseline. All right, so. Let's a little bit of history here. Over 2,300 years ago, there was a guy named Eratosthenes, a very famous Greek, who actually lived in Alexandria. He was the chief librarian for the great library in Alexandria, and he actually heard. Or not heard. He read in the library that there was this town at the bottom of the Nile called Syene, that on a certain day, which happened to be the first day of summer, that a well would cast no shadow, that the sun was directly overhead, and he realized that he could use that knowledge and the knowledge of geometry to actually measure the circumference of the Earth. And he measured the shadow that an obelisk would make at Alexandria, and he paid somebody to walk all the way from Alexandria to Syene and back, of course, because he had to give him that information, give Eratosthenes that information. We don't know who the person is that walked that distance, but anyhow, with that information and then the knowledge in measuring that angle, which turned out to be a little more than 7 degrees, Eratosthenes was able to measure the circumference of the Earth and got a pretty good number. I mean, it's within 20% of the modern value. So that's actually pretty amazing for something more than 2,000 years ago to come up with this. Using geometric arguments, the fact that the sun is so far away that the rays of light were parallel. So the sunlight that hit Alexandria and the sunlight that hit Syene on the he had to measure the angle, of course, on the same day. And of course the ancients knew very well when the longest day of the year was. So let's say at noon on that day, when the sun was as high in the sky as it was going to get, he knew that at Syene there was no shadow, and then at Alexandria he measured the shadow, and then he knew that was part of the circle, and then knowing the distance between the two, he could actually measure the circumference of the Earth, right, by just knowing the distance between the two and knowing what that angle was. All right, that concludes the chapter 1, and so all right, so chapter 1 and chapter 2 will be on the first test. I will talk about chapter 2 next.